All right, in this video, we're going to be talking about a specific math skill for AP biology. We're going to be talking about water potential and solute potential. We're going to talk about how to calculate it. We're going to try to build on what you already know and why water potential is important for life. So first, we need to understand a concept related to osmosis or the movement of water. And specifically, we should understand these vocab words. We should understand isotonic, hypertonic, and hypotonic. We should understand the difference between these solutions in a plant cell versus an animal cell as well. I'm going to cover the basics of it in this video, but for a more detailed explanation, you'll have to watch one of my other videos. Okay, so let's start with animal cells and hypotonic. So hypo means low. Think of hypothermia. Hypothermia means you're really cold or you have low temperature. So hypo means low. Tonic means solute. So that's something that's dissolved in water. In this case, the solution is hypotonic. So that means that there's actually more solute. I'm representing that with these dots. There's actually more solute inside the cell than there is on the outside. So there is some on the outside, but not as much as on the inside. As a result, water is going to flow into the cell. For the reason behind that, you'll need to watch my other video on tonicity. But the water will flow into the cell. Because water is flowing into the cell, animal cells will eventually burst if enough water flows in because they don't have a cell wall like a plant cell does. The opposite is true in a hypertonic solution. So hyper means lots, right? Like think about someone who's hyper, they have lots of energy. And tonic, again, is talking about solute. So hypertonic solution has lots of solute surrounding the cell. So there's lots of solute dissolved in the water on the outside, not very much on the inside. As a result, the water is going to flow out of the cell. The cell is going to shrink. Isotonic, iso is actually referring to equal. So there's actually an equal amount of solute on the inside and the outside of the cell. As a result, water is going to flow out and it's going to flow in equally, or this cell would be in equilibrium. It's slightly different for plant cells, but very similar. Again, watch my tonicity video for more info on that. All right, so then what is water potential? What are you actually going to have to do? We'll first have to understand the basics about it. We'll learn how to calculate water potential and use it to determine how likely it is that water will move into or out of a cell. And that's what water potential is. It's a measurement of how likely it is that water will move in or out of a solution. We'll talk about why pure water is assigned a potential of zero, a water potential of zero. And we'll also talk about why the more negative the water potential, the more likely water will move into that area. We'll look at this equation in more depth in a later video, but the first part here is just understanding the basics. So water potential is given the Greek letter psi. Think about like Poseidon, a trident, and there is representing water potential. It's equal to the pressure potential and the solute potential added together to get the water potential. So we'll talk about each of these measurements individually, but first we need to understand conceptually how water potential works, and then we'll get into the equations. Well, one big concept that's important to understand, and we'll understand the why later, but for now, just bear with me that the water potential of pure water in an open container is equal to zero. So pure water is given the zero because one, if you're in an open container, there is no pressure that can build up. And pure water, there's no solute in it. So that has to be equal to zero as well. And so the pure water is given zero. And we'll understand the significance of that in a moment. The next big thing to understand is that water will flow from an area of higher water potential to an area of lower water potential. So I'm going to back up to something you probably learned in another one of my videos, and that is that water in osmosis, so we can think about osmosis, another related process here. Osmosis is the measurement of or the movement of water across a semi-permeable membrane. And water will always move passively from high to low concentration. So wherever there's more water, water will flow from where there's more to where there's less. The same idea is true here for water potential. So water potential, I'm not going to use the symbol for water potential. Water will also move from a high water potential to a low water potential. We use the bigger version here to show that, but this is a great diagram to think about that. And the reason I use that diagram is because I like to think about it like a ball. And let's say this is a hill, and this hill is high up, and the bottom of the hill is low. If I have a ball on top of the hill, it's going to flow from high to low, and it's the same for water and water potential. All right. We can try to use that basic concept to understand this practice question. Well, first off, we want to know which way will water flow. Is it going to flow into the cell? Is it going to flow out of the cell? And I'm just going to give you some couple hints. Well, one, it's an open container, and the water potentials are actually already given to you. So here's the water potential of the cell. So this is actually a cell, and this is just the water itself here. And there's our water potentials. Okay, go ahead and pause the video and see if you can answer it. All right, if you pause the video, many of us would have said that the water is going to flow, right, to the bigger number because we know that water potential will flow from where there is a high water potential to a low water potential. To actually understand this in more depth, though, we need to think about these numbers. Notice the negative sign that's in front of both of these numbers. That negative is actually important when we're thinking about this. We actually need to think about water potential like a number line. So if I were to give you the number 0 and ask you which number is bigger, 0 or negative 2.5? Maybe that's a little bit hard to start with. Why don't we say which number is bigger, 0 or 100? And you would say, well, 100 is definitely bigger than 0. And that's because it is a more positive number, right? 100 is a more positive and larger number than 0. If we use that same school of thought, 0 then is actually a larger and more positive number than negative 2.5. And using that same thought, that means that negative 0.5 is actually a bigger number than negative 2.5. So with all of that in mind, we can look back at our numbers. So we know that this number is actually a larger number than this number. Therefore, we know that water potential is going to move from where there's a higher one to a lower one. So negative 0.5 is a higher number than negative 2.5. So the water is going to flow from high to low. So it's going to flow into the cell. Here's a more detailed explanation. First, erase this. Let's see if I can get that detailed explanation. There we go. So if you want to pause the video, you can fully read in on this as to why. Okay. The last part, we can see why is this important for life? How does this play into life on Earth and how water moves? And so we can see in this example, we have a tree and we can see the water potential. So in the soil, the water potential is negative 0.3. Okay. And in the outside air, the water potential is actually negative 100. And so this explains how trees can get water from their roots, fight it up against gravity, and pull that water all the way through its body. If we look at each step of the way, the water potential is actually becoming more negative. So what does that mean? Remember that water potential will go from a high water potential to a low water potential. Why don't you pause the video? Where is there a higher water potential in this plant? Is it in the soil or is it in the outside air? If you paused it, you probably noticed that the soil has relatively a larger water potential because using our number line idea, negative 0.3 is a more positive number than negative 100, right? And so the outside air has a lot lower water potential, and each step of the way has a lower water potential. So it's going to pull that water to each sequence of the tree. And that explains why eventually the trees will lose that water to the outside air. All right, hopefully that helps, and looking forward to talking in the next video.